Hello everyone, this is Chinnaiah Kalpana here. In this video, we're going to solve a differential equation using integrating factor. So let's get going. Problem: solve y square plus 2x square y dx plus 2x cube minus xy into dy equal to 0. So we have noticed the given differential is of the form mdx plus ndy equal to 0, right? The standard form. The given differential equation is given differential equation y square plus 2x square y into dx plus 2x cube minus xy into dy equal to 0. Consider as equation 1, which is of the form, the standard form mdx plus ndy equal to 0. Let's see whether the given differential equation is exact or not. So that we have to find, for that we have to find partial derivative of m with respect to y and partial derivative of n with respect to x. If the partial derivative of m with respect to y equal to partial derivative of n with respect to x, then we can say that the given differential equation is exact. Okay. I'll begin with partial derivative of m with respect to y. Here m is the quotient of dx, y square plus 2x square y, and n is quotient of dy, that is 2x cube minus xy. Let's now find the partial derivative of m with respect to y is equals to partial derivative of y square with respect to y, or let's write one more step for our convenience. So here we are doing partial derivative with respect to y, so x is treated as constant. In the second step, in the second term 2x square is constant, so let's write it outside the brackets. So you can reduce the steps. Is equals to partial derivative of y square with respect to y is 2y plus 2x square into partial derivative of y with respect to y is 1, which gives us 2y plus 2x square. Let's now find partial derivative of n with respect to x. N is 2x cube minus xy. This equals to partial derivative of first term minus partial derivative of second term. Here we are finding partial derivative with respect to x, so y is treated as constant. Here 2 is constant and y is constant in the second term. So let's write that outside the brackets. Just we'll get 2 times partial derivative of x cube minus constant into partial derivative of x, which gives us 2 into partial derivative of x cube with respect to x is 3x square minus y into partial derivative of x with respect to x is 1, which gives us 2 3 is 6 x square minus y, right? It is clear that partial derivative of m with respect to y is not equals to partial derivative of n with respect to x. Therefore, partial derivative of m with respect to y is not equal to partial derivative of n with respect to x, which shows that equation 1 is not exact. Now, just consider the given differential equation y square plus 2x square y into dx plus 2x cube minus xy into dy equal to 0. And we can write this as y square dx plus 2x square y dx plus 2x cube dy minus xy dy equal to 0, right? Now if you notice, we can take y common from these two terms and x square common from these two terms. So I'll write the first term and the last term firstly. Now I'll write the remaining two terms. Right, now I'll take y common from the first two terms, so I'll get y times y dx minus x dy plus, now I'll take x square from common from the next two terms, I'll get x square times 2y dx plus 2x dy equal to 0, right? Or we can write this equation as, here you are having y, right? We can write y as y power 1, and here we don't have any x terms, so we can write x power 0 into y, right? We can write like this, right? Or we have y, we can write y as y power 1, or we can write as 1 into y power 1. We can replace 1 by x power 0 since x power 0 equal to 1, right? So we'll get x power 0 into y power 1. So we'll write this y as x power 0 y power 1 for our convenience, okay, into the terms under brackets plus, in the second term you're having x square and you don't have any y term here, so I'll write x square as x into 1, and I'll replace this 1 with y power 0 since y power 0 is 1, right? So I can replace 1 by y power 0, so I'll get x square into y power 0. Now I'll replace this x square by x square y power 0 into 2y dx plus 2x dy equal to 0. I'll consider it as equation number 2, which is of the form x power a y power b into my dx plus nx dy plus x power c y power d into py dx plus qxdy equal to 0. So we can write the given differential equation in this form, right? We wrote the given differential equation in this form. By comparing these two, we'll get a, b, m, n, c, d, p and q, right? Since we have written the given differential equation in this form, so here our integrating factor will be x power alpha and y power beta. Where a equal to 0, b equal to 1, m equal to 1, n equal to minus 1, c equal to 2, d equal to 0, d 0, p 2, q 2. Right? Since the given differential equation can be written in this form, so here x power alpha, y power beta is the integrating factor. Let x power alpha, y power beta be the integrating factor. Integrating factor of equation 1, that is the given differential equation. Now we'll find alpha and beta, and later we'll multiply the real integrating factor to the given differential equation to make it exact, and then we'll find the general solution to the given differential equation. Let x power alpha y power beta be an integrating factor of 1. Multiplying. Now we'll multiply this integrating factor to 1. Multiplying 1 by the integrating factor x power alpha y power beta. Just multiply the integrating factor to the given differential equation. Y square plus 2x square y into dx plus 2x cube minus xy into dy equal to 0. This gives us x power alpha y power beta into y square plus 2x square y into dx plus x power alpha y power beta into 2x cube minus xy into dy equal to 0, right? This gives us x power alpha into y power beta y square dx plus, alright, plus 2 x power alpha x square into y power beta y into dx plus 2 x power alpha x cube y power beta minus x power alpha x y power beta y into dy equal to 0, right? Now we can write this as x power alpha y power beta into y square gives y power beta plus 2 plus 2 x power alpha into x square gives us x power alpha plus 2 y power beta into y gives us y power beta plus 1 into dx plus 2 into x power alpha into x cube gives us x power alpha plus 3 into y power beta minus x power alpha into x gives us x power alpha plus 1 and y power beta into y gives us y power beta plus 1 into dy equal to 0. Consider as equation asterisk. This equation is exact if asterisk is exact if partial derivative of m, right? Since this is of some mdx plus ndy equal to 0 form, right? So this is exact if partial derivative of this term, that is x power alpha y power beta plus 2 2x power alpha plus 2 into y power beta plus 1 with respect to y is equals to partial derivative of the expression, the quotient of dy 2x power alpha plus 3 y power beta minus x power alpha plus 1 y power beta plus 1. Okay, asterisk, that is the equation asterisk is exact if partial derivative of this expression with respect to y is equals to partial derivative of this expression with respect to x, right? This gives us, or we can write this as partial derivative of first term x power alpha y power beta plus 2 plus partial derivative of second term 2x power alpha plus 2 y power beta plus 1 equal to partial derivative of first term of RHS 2x power alpha plus x power alpha plus 3 into y power beta minus partial derivative of x power alpha plus 1 y power beta plus 1. In LHS, we are doing partial derivative with respect to y. So x is treated as constant in the first term, x power alpha is constant. In the second term, 2 x power alpha plus 2 is constant. In RHS, we are going to find partial derivatives with respect to x. So we'll treat y as constant. So in the first term of RHS, 2 y power beta is constant. In the second term of RHS, y power beta plus 1 is constant, right? Now we can write this as x power alpha into partial derivative of y power beta plus 2 plus 2x power alpha plus 2 into partial derivative of y power beta plus 1 equal to 2y power beta into partial derivative of x power alpha plus 3 minus y power beta plus 1 into partial derivative of x power alpha plus 1, right? Which gives us x power alpha into partial derivative of y power beta plus 2 with respect to y is beta plus 2 into y power beta plus 2 minus 1 plus 2x power alpha plus 2 into partial derivative of y power beta plus 1 with respect to y is beta plus 1 into y power beta plus 1 minus 1 equal to 2 y power beta into partial derivative of x power alpha plus 3 with respect to x is alpha plus 3 into x power alpha plus 3 minus 1 minus y power beta plus 1 into partial derivative of x power alpha plus 1 with respect to x is alpha plus 1 into x power alpha plus 1 minus 1, right? This gives us x power alpha, okay, x power alpha of beta plus 2 into y power beta plus 2 minus 1 is plus 1 plus 2x power alpha plus 2 into beta plus 1 into y power beta plus 1 minus 1 is 0, right? You'll get just y power beta here. Plus 1 minus 1 gets cancelled, right? This is equals to 2 y power beta into alpha plus 3 into x power alpha plus 3 minus 1 is plus 2 minus y power beta plus 1 into alpha plus 1 into x power, if plus 1 minus 1 gets cancelled, you'll get x power alpha. This gives us beta plus 2 into x power alpha y power beta plus 1 plus 2 times beta plus 1 into x power alpha plus 2 y power beta equal to 2 times alpha plus 3 into x power alpha plus 2 y power beta minus alpha plus 1 into x power alpha y power beta plus 1. Now let's equate the quotient of x power alpha y power beta plus 1 and equate the quotients of x power alpha plus 2 y power beta. Okay, equating coefficient of x power alpha y power beta plus 1, which gives us beta plus 2 equal to minus of alpha plus 1, right? We'll get beta plus 2 equals to minus alpha minus 1. Now bring this minus alpha to LHS and take this 2 to RHS. We'll get alpha plus beta equal to minus 1 minus 2, which gives us alpha plus beta equal to minus 3. Consider it as equation number A. Now equating coefficients of x power alpha plus 2 y power beta, which gives us 2 times beta plus 1 equal to 2 times alpha plus 3, right? We'll get 2 beta plus 2 equal to 2 alpha plus 2 3 is 6. Now bring this to alpha to LHS, or better you can just write this as 2 alpha plus 6 equal to 2 beta plus 2, right? Now bring this 2 beta to LHS, take this 6 to RHS, we'll get 2 alpha minus 2 beta equal to, so here you can cancel 2's, okay? This gives us beta plus 1 equal to alpha plus 3. Now bring this alpha to LHS, or you can write the above equation as alpha plus 3 equal to beta plus 1. Now bring this beta to LHS and take this 3 to RHS. We'll get alpha minus beta equal to 1 minus 3, which gives us alpha minus beta equal to minus 2. Consider as equation B. Now by solving these two equations, we'll get A and B. Solving A and B to find alpha and beta, okay? Alpha plus beta equal to minus 3, alpha minus beta equal to minus 2. Here plus b minus b gets cancelled, you'll get 2 alpha equal to minus 3 minus 2 is minus 5. From this we'll get alpha equal to minus 5 by 2, right? Now substitute this alpha in equation A, since we are having alpha plus beta equal to minus 3. We can write this as beta equal to minus 3 minus alpha. Now substitute alpha here, we'll get minus 3 minus of minus 5 by 2, which gives us 2 3 is 6, that is minus 6, minus into minus plus 5 by 2, which is minus 1 by 2. So therefore beta is minus 1 by 2. Therefore alpha equal to minus 5 by 2, beta equal to minus 1 by 2. Now we got alpha and beta, and let's now find the integrating factor by substituting alpha and beta and x power alpha and y power beta. Now the integrating factor becomes x power alpha into y power beta equal to, we have alpha and beta values, right? Just substitute it. We'll get x power minus 5 by 2, y power minus 1 by 2, right? Therefore x power minus 5 by 2 into y power minus 1 by 2 is the integrating factor. Now multiplying 1 by this integrating factor gives y square plus 2x square y into dx plus 2x cube minus xy into dy equal to 0, right? Or we can write this as x power minus 5 by 2, y power minus y by 2, x power minus 5 by 2, y power minus 1 by 2 into y square plus 2x square y into dx plus x power minus 5 by 2 into y power minus 1 by 2 into 2x cube minus xy into dy equal to 0. Or we can write this as x power minus 5 by 2 into y power minus 1 by 2 into y square plus 2 x power minus 5 by 2 into x square y power minus 1 by 2 into y into dx plus 2 x power minus 5 by 2 into x cube y power minus 1 by 2 minus x power minus 5 by 2 into x y power minus 1 by 2 into y into dy equal to 0, or x power minus 5 by 2 into, we can write y power minus 1 by 2 into y square as y power minus 1 by 2 plus 2, right? Plus 2 into, we can write x power minus 5 by 2 into x square as x power minus 5 by 2 plus 2, and y power minus 1 by 2 into y can be written as y power minus 1 by 2 plus 1, just add the powers, plus 2 into x power minus 5 by 2 plus 3 y power minus 1 by 2 minus x power minus 5 by 2 plus 1 y power minus 1 by 2 plus 1 into dy equal to 0. This becomes x power minus 5 by 2 y power minus 1 by 2 plus 2 gives us minus 1 plus 2 2s are 4 by 2, which is 4 minus 1 3 by 2. You'll get 3 by 2 here, plus 2 into x power minus 5 by 2 plus 2 gives us minus 5 plus 2 2s are 4 by 2, which is minus 1 by 2 into y power 1 by 2 minus 1 by 2 plus 1, 1 minus half is half into dx plus 2 into x power minus 5 by 2 plus 3 gives us minus 5 plus 3 2s are 6 by 2, which gives us 1 by 2 y power minus 1 by 2 minus x power minus 5 by 2 plus 1 gives us minus 5 plus 2 by 2, which is minus 3 by 2 into y power minus 1 by 2 plus half is half, that is 1 by 2, sorry, 1 minus half is half otherwise, right, into dy equal to 0. Now consider this equation as equation number 3, which is of the form, say, sum m1 dx plus n1 dy equal to 0, where m1 equal to x power minus 5 by 2 y power 3 by 2 plus 2x power minus 1 by 2 y power 1 by 2, and n1 equal to 2x power 1 by 2 y power minus 1 by 2 minus x power minus 3 by 2 y power 1 by 2. Now we can say that equation 3 is exact if partial derivative of m1 with respect to y equal to partial derivative of n1 with respect to x. So let's now find the partial derivatives of m1 and n1. I'll begin with partial derivative of m1 with respect to y is equals to dou by dou y of m1 x power minus 5 by 2 into y power 3 by 2 plus 2x power minus 1 by 2 into y power 1 by 2, right? Which gives us, or we can write this as 2 dou by dou y of first term plus dou by dou y of second term. Since it is a partial derivative with respect to y, so we'll treat x as constant. Here x power minus 5 by 2 is constant, and in the second term 2x power minus 1 by 2 is constant. So let's take this out of the bracket, so we'll get it. You can write this as minus x power minus 5 by 2 into dou by dou y of y power 3 by 2 plus constant 2x power minus 1 by 2 of partial derivative of y power 1 by 2, which gives us x power minus 5 by 2 into partial derivative of y power 3 by 2 with respect to y is 3 by 2 into y power 3 by 2 minus 1 plus 2x power minus 1 by 2 into partial derivative of y power 1 by 2 is 1 by 2 into y power 1 by 2 minus 1, which gives us 3 by 2 x power minus 5 by 2 into y power 3 by 2 minus 1 is 1 by 2 plus here 2 gets cancelled and you'll get x power minus 1 by 2 y power 1 by 2 minus 1 is minus 1 by 2. Therefore, partial derivative of m1 with respect to y equal to 3 by 2 x power minus 5 by 2 into y power 1 by 2 plus x power minus 1 by 2 into y power minus 1 by 2. So we got partial derivative of m1 with respect to y. Let's now find partial derivative of n1 with respect to x. Dou by dou x of n1, 2x power 1 by 2 y power minus 1 by 2 minus x power minus 3 by 2 y power 1 by 2. Or we can write this as dou by dou x of first term minus dou by dou x of second term. Since we are doing partial derivative with respect to x, so y is treated as constant. Here in the first term 2 y power minus 1 by 2 are constants, and in the second term y power 1 by 2 is a constant, right? Let's write the constants outside the brackets. We will get 2 y power minus 1 by 2 into partial derivative of x power 1 by 2 minus y power 1 by 2 into partial derivative of x power minus 3 by 2, which gives us 2 y power minus 1 by 2 into partial derivative of x power 1 by 2 with respect to x is 1 by 2 into x power 1 by 2 minus 1 minus y power 1 by 2 into partial derivative of x power minus 3 by 2 with respect to x is minus 3 by 2 into x power minus 3 by 2 minus 1, right? Which gives us, here 2 gets cancelled, we'll get y power minus 1 by 2 into x power 1 by 2 minus 1 is minus 1 by 2, right? You'll get x power minus 1 by 2 minus into minus plus 3 by 2 into y power 1 by 2 into x power minus 3 by 2 minus 1. Gives us minus 5 by 2, right? Or we can write this as 3 by 2 x power minus 5 by 2 y power 1 by 2 plus x power minus 1 by 2 y power minus 1 by 2. So if you notice, partial derivative of m1 with respect to y is equal to partial derivative of n1 with respect to x, right? Therefore, partial derivative of m1 with respect to y equal to partial derivative of n1 with respect to x equal to 3 by 2 x power minus 5 by 2 y power 1 by 2 plus x power minus 1 by 2 y power minus 1 by 2. This shows that equation 3 is exact. Therefore, the general solution to equation 3 is given by integral over y m1 dx, that is treating y as constant, plus integral n1 terms of n1 free from x into dy equal to c, right? Let's now find the first integral and second integral. Integral m1 dx treating y as constant, this is equals to integral m1 x power minus 5 by 2 y power 3 by 2 plus 2x power minus 1 by 2 y power 1 by 2 into dx treating y as constant. So in the first term y power 3 by 2 is constant, in the second term 2 y power 1 by 2 is constant, right? So let's write the above integral as y power 3 by 2 into integral x power minus 5 by 2 into dx plus 2 y power 1 by 2 integral x power minus 1 by 2 dx, which gives us y power 3 by 2 into integral x power minus 5 by 2 dx is x power minus 5 by 2 plus 1 by minus 5 by 2 plus 1 plus 2 y power 1 by 2 into integral x power minus 1 by 2 dx is x power minus 1 by 2 plus 1 by minus 1 by 2 plus 1. This gives us minus 5 by 2 plus 1 is minus 5 plus 2 by 2, this is equals to minus 3 by 2, and minus 1 by 2 plus 1, that is 1 minus half is half, right? Or okay, so we'll get y power 3 by 2 into x power minus 3 by 2 by minus 3 by 2 plus 2 into y power 1 by 2 into x power half by 1 by 2. This gives us minus 2 by 3 x power minus 3 by 2 y power 3 by 2 plus 2 into 2 into x power 1 by 2 y power 1 by 2, right? Now we can write x power minus 3 by 2 as 1 by x power 3 by 2 into y power 3 by 2 plus 2 into 2, right, 4 x power 1 by 2 y power 1 by 2, which gives us minus 2 by 3 into y power 3 by 2 by x power 3 by 2. See, 1 by x power 3 by 2 into y power 3 by 2 gives us y power 3 by 2 by x power 3 by 2 plus 4 x power 1 by 2 y power 1 by 2. Or we can write this as minus 2 by 3 into y by x whole power 3 by 2 plus, since we know that a power 1 by 2 can be written as square root of a, then we can write square root of, x power 1 by 2 as square root of x and y power 1 by 2 as square root of y. Or we can write this as minus 2 by 3 into y by x power 3 by 2 plus 4 into square root of x into square root of y can be written as square root of xy, right? Therefore, integral m1 dx treating y as constant is 4 root xy minus 2 by 3 into y by x whole to the power 3 by 2. Now let's find the second integral. Integral n1 terms of n1 free from x into dy. Now consider, just look at n1. In n1 we don't have terms which are free from x, right? In both the terms we have x. So integral n1 terms of n1 free from x is 0. Now coming to the general solution. the general solution to 3 is so the result obtained from M1 is 4 into square root of xy minus 2 by 3 into y by x whole to the power 3 by 2 plus result obtained from the second integral is 0 equal to c, which gives us 4 into square root of xy minus 2 by 3 into y by x whole power 3 by 2 equals to c. Now we can just consider it as equation or take 2 common from these two terms, we'll get 2 times 2 root xy minus 1 by 3 into y by x whole to the power 3 by 2 equal to c. Now take the LCM of these two, we'll get 3 2s are 6 square root of xy minus y by x whole power 3 by 2 equal to c, or we can write this as 2 into 1 by 3 into 6 root xy minus y by x whole power 3 by 2 equal to c, or 2 into 1 by 3 is 2 by 3 of 6 into square root of xy minus y by x power 3 by 2 equal to c, or take this 2 by 3 to RHS, then we'll get 6 root xy minus y by x whole to the power 3 by 2 equal to c into 3 by 2, right? Or if you take this to RHS, you'll get 1 by 2 by 3, which gives us 6 into square root of xy minus y by x power 3 by 2 equal to c into 3 by 2. Let c into 3 by 2 be some c, which gives us 6 square root of xy minus y by x power 3 by 2 equal to c, which is the required solution. Therefore, the required solution is 4 into square root of xy minus 2 by 3 into y by x power 3 by 2 equal to c, or 6 into square root of xy minus y by x power 3 by 2 equal to c, where c equal to 3 by 2 into c. So we have seen a problem from differential equations using integrating factor in this video. I hope you'll understand. We'll see you in the next video. Until then, bye bye.